Hello, everyone. My name is Shimaa. I'll be presenting our work on robust keyword spotting. This work is done in collaboration with Ilia, Nicolas Papernot from University of Toronto, and my advisor, Kassem Fawaz. Voice assistants are becoming widely popular. We all have interacted with at least one of them at some point, like Amazon Echo, Google Home, Cortana, Siri, Google Assistant. Voice assistants enable a voice-based and hands-free interaction, and that which makes them favorable in many situations, like during cooking, driving, during workout. Some recent statistics show that there have been about 4.2 billion devices in 2021. And in 2022, Amazon reported that Alexa receives billions of interactions every week, which confirms the scale at which these devices are deployed. The general pipeline of any voice assistant is as follows. It starts by a microphone, which is always on, always listening to the environment, and feeding the detected speech to the keyword spotting module. The keyword spotting processes the speech locally on the device, looking for the keyword, the activation keyword, Alexa, for example. If the activation word is detected, the device records and sends the subsequent command to the cloud for transcription and then for execution by the natural language understanding unit. Voice assistants are well integrated in the modern environments. They control home appliances, they make purchases, transactions, initiate a call, enable a third-party skill, which makes them very powerful. For example, if a user says, Alexa, open the garage door. Once the activation keyword Alexa is spotted, the rest of the pipeline gets activated, and then the garage door will be opened. So the keyword spotting is the main access control mechanism to the voice assistant, which makes it the gate to control all the next subsequent appliances and skills. The baseline architecture for keyword spotting is actually a convolutional neural network whose input features are the spectrograms of the input speech. So it's similar to image recognition. So keyword spotting is just a machine learning detector, and detectors make mistakes. In this work, we consider two settings or two threat models where the keyword spotting gets falsely activated and enable unauthorized access to the voice assistant. The first threat model is accidental activation, where the keyword spotting model confuses a phrase with the activation keyword. For example, OK Google can be confused by OK to go. It's not the same word, but it's close, so the keyword spotting can be confused and get activated. In this case, the device records private conversations because it's listening to conversation that is not intended to be a command, and send the conversations to the cloud, and that compromises the user privacy. In our evaluations, we found that these false activations can last for up to 80 seconds. The second threat model is adversarial activations, which involves an adversary who crafts adversarial examples to maliciously activate the device and gain access to the connected appliances and skills, which compromises the integrity and safety of the user and the device. To address these two threat models, we will present EKOS, an ensemble for robust keyword spotting. So EKOS relies on the existing smart devices in the environment. In any modern environment, we have a set of smartphones, tablets, laptops, and all these devices have microphones and have computation and communication modules. So EKOS relies on them to perform ensemble learning. It exploits different sources of diversity to make the ensemble actually work. For example, these devices are independently and randomly placed in the user environment, and each device experiences a unique acoustic channel and has its own hardware fingerprint. EKOS also introduced diversity by enabling multiple machine learning architectures. So each of those devices can deploy a different architecture. So we have different sources of diversity that will lead to a successful ensemble learning. So each device will independently perform keyword spotting and send the vote to the main voice assistant, which performs a majority vote. And based on the score of the majority vote, it detects whether the received speech contains the keyword or not. The detailed operation is as follows. Again, each device receives a copy of the spoken utterance shaped by the room reverberation, which is usually in literature called room impulse response. It's just a mathematical formulation of how the room shapes the acoustic signal, and performs feature extraction, selects the architecture, performs the keyword spotting and decides on the vote, and then send the vote to the main voice assistant. So deploying EKOS in our evaluations showed that EKOS improves the accuracy with up to 20% compared to any single device. Under the adversarial threat model, a simple ensemble is not enough. So EKOS adds another layer of randomness, which is feature slicing. Each device will randomly slice the input spectrogram into small frequency bands and perform the keyword spotting using these limited input features. It will not perform keyword spotting on the whole band. It will select a small subset. So feature slicing can be defined as a random transformation that make the adversarial optimization more constrained, which will lead to a larger perturbation and hence higher attack perceptibility. Even if the attack succeeds, it will have higher perceptibility. So that will make it not an adversarial example. It will be obvious to the users. And our evaluations showed that EKOS improves the adversarial accuracy with up to 30%. We evaluate EKOS under two setups. The first one is open source implementation using commodity devices like normal off-the-shelf smartphones and laptops, and open source dataset, which is Google Commands. And the second is we actually implement EKOS on commercial voice assistants. We select Amazon Echo because it can be activated by 4 different keywords. Now, actually, they are 6, but at the time we did the experiments, they were only 4. So we could do extensive evaluations. I'll start by the open source implementation. So we selected those 12 labels from the Google Commands dataset, and we trained different keyword spotting architectures, deployed the model on 6 devices, again, including smartphones, laptops, an iPad, a PC connected to a professional microphone. This figure shows the keyword spotting accuracy of each individual device from D1 to D6 under different background noise situations, and then EKOS performance as well at ensemble size of 3, 5, and 7. And as you see from the figure, EKOS outperforms all the individual devices with up to 20%. Under the adversarial setting, we generated 90 adversarial examples. Those are successful adversarial examples generated on the architectures we trained. And we tested them on the same setup using PGD and PGD-RIR attack. And PGD-RIR attack is just a more sophisticated attack that considers the environment as well in generating the adversarial examples. And again, we found that EKOS outperforms all the individual devices with up to 30% accuracy boost. Second, we evaluated EKOS on the commercial voice assistants, again, Amazon Echo. Since there are no public data sets for Amazon Echo or even any commercial device, we created our own data set for the 4 keywords that can activate Echo Dot. We extracted the positive samples from public speech data sets and also by using speech synthesis. And for the negative samples, generally speaking, any speech that does not contain the keyword is a negative sample, but we wanted to test the negative samples that are highly likely to falsely activate the device. So we relied on 2 recent studies who actually did this evaluation and found the phonetically close words for each of those keywords, and we used their data sets. We used 4 Echo Dot devices and 1 Echo Tower, which is the first generation of Amazon Echo, in a lab, in our lab environment. And we played the data set over the air and recorded the activation rate of each individual device. And we found that EKOS, when we have the 5 devices contributing to the ensemble, reduces the false activation rate with up to 50%. So this reduction is in the accidental activation setting and also the adversarial setting. So in summary, we designed 2 complementary approaches to tackle 2 threat models. The first is the non-machine learning part, which does the feature slicing and over-the-air randomness. And this part mainly addresses the adversarial examples. And the second part is the ensemble of different architectures, and that part helped with the accidental activation. So those 2 approaches combined could tackle the 2 threat models. Thank you for listening to the talk. I think I made a record for finishing really fast. And I'm ready to answer any questions.